Okay, so last time we have seen that product topology, right? And no, not product, subspace topology, right? And product topology as well for two or finite number of product. Okay, so today I shall start with some basic results. Okay, so is that is recording? Yeah, fine. Okay, so we have seen that if X is a topological space and if Y is a subspace of that topological space, then U is open in Y, right? If and only if there exists an open set, say V in X such that U equal to V intersection Y, right? It is just the definition of subspace topology. Now, in similar notation, we will prove now by using this one. So if Y subset of X, that's mean a subspace of X, then a set C is closed in Y if and only if C equal to some D intersection Y, where D is closed in X. Okay, so we prove this theorem by using this. Fine. So first of all, let C is closed in Y. Okay, and we will prove that C equal to some D intersection Y. Okay, now what does it mean by C be a closed set in Y? So that's mean Y minus C is open in where? Y, right? Now we use this definition. So that imply there exists say U which is open set in X such that Y minus C equal to U intersection Y. Okay. Now since U is open in X, now that implies X minus U is closed in X, right? Now let D equal to this one, this closed set, say X minus U. Now then, what is D intersection Y? Can you see that D intersection Y is actually C? Okay, so what is that? This is just X minus U intersection Y, which is just Y minus U, right? And what is Y minus U? Which is same as Y minus U intersection Y as well, because we are subtracting from Y, right? So therefore it is U minus, right? Now what is my U intersection Y? This is
Y
Y
minus
minus
C.
C, right? So it is Y minus C. So it is Y minus C. So this is just C. So we are done. That is a simple one. Now conversely, you can also prove that. Now conversely, you can also prove that. So let say A equal to C intersection Y, where C is say closed in X. Okay, so we need to prove that A is closed in Y. So what will show? So claim A is closed in Y, and which is equivalent to saying that Y minus A is open in Y, and which is again equivalent to saying that there exists open set U in X such that Y minus A equal to U intersection Y. Okay, so we need to find such Y, such U. Now can you guess so what should be your U? Any guess?
X minus C.
Right, so that is simple. Now now this is my claim actually. So U equal to X minus C, and then U intersection Y equal to X minus C intersection Y, that is Y minus C, right? So what is now Y minus C? Now what you need to prove that? Right, now again in the similar note, X minus that is C intersection Y, and what is C intersection Y? We have written somewhere, right? Now that is A. So that is Y minus A. So we are done. So that is very simple one, right? Any problem on this? That is very simple. That's mean from now onwards you can say that if Y is a subspace of X, then any set A is closed in Y if and only if there exists a closed set C in X such that A equal to C intersection Y, right? And similarly, and we know this is for true, this is true for open set as well, right? That was the definition, and by using that definition we prove that is true for the closed set as well. Right, now we know another definition of closed set, that is a set is said to be closed if A equal to a closure, right? So last time we defined that closure as well. Now we prove the similar statement here for the subspace topology. Okay, so again say let Y be a subspace topology in X of X. Subspace. Okay, now then we prove that actually so first of all, so let a closure denote the closure of a set A in X. Okay, now then we prove that closure of A in Y is a disclosure intersection Y. Did you get the statements? So Y is a subspace of X, and A closure, that is A closure denote the closure of A in X. Then what will be the closure of A in Y? That is this. We will prove that. Okay. Now what is the definition of closure? Do you remember that? What is the definition of closure of a set A?
A bar equal to A union derived set of A.
Ah, that was a different one. Which definition I used last time in the last lecture?
It is the smallest closed set containing A.
Right. So you will use that definition because we define in that way. Okay. So here is the proof. So first of all, let B be the closure of A in Y. Okay. And we claim that B equal to A closure intersection Y. Now how to prove this? So first of all, we use the property of B, that is which is the smallest closed set containing A in Y, and again we will use the property of A closure, which is the smallest closed set containing A in X. Okay. And then we will see that this subset of this subset of this, so both are equal. Okay. Right. So first of all, so let B be the closure of A in Y. So we assume first this. Okay. Now since B be the closure of the offset E, that's mean B is a closed set, right? Containing A in Y, right? Now what does it mean? B is a closed set containing A in Y. That's mean there exists a closed set C Okay, so first of all here I should write another thing. So A is a subset of Y. Otherwise there is no meaning of saying that. Okay, A subset of Y. Okay. Now first of all, right. So that implies there exists a, since B is a closed set, so there exists a closed set C in Y such that B equal to C intersection Y. Right? So that implies A, which is subset of B because B is the closed subset, and C intersection Y. Now that implies A subset of C. Okay. Now A subset of C and C is a closed set.
Sir, there exists closed set in X things.
Ah, sorry. Good. Hmm. Oh, no. Sorry. I missed that one. So this is B is a closed set in Y and there is a closed set C in X. Good. Right. Now this, right? Now since C is a closed set in X containing A and A closure is the smallest closed set in X containing A. So therefore we have A closure subset of C. Now that implies A closure intersection Y subset of C intersection Y. And what is C intersection Y? That is B. So that implies we have this one. A closure intersection Y subset of B. So is this part clear? Fine with everyone? We just use the property of A closure is the smallest one. So we get this. And next we will use the property of B. See here we did not use the property of B that B is the smallest open set. We use just the property that B is a closed set. Okay. Now conversely. Okay. Now since a closure is a, see remember I am not using a closure is a is a closed set. Is a closed set in X containing A and a subset of Y. So that implies a closure intersection Y is a closed set in Y containing A. Okay, but we know that B is the smallest closed set in Y containing A. So that implies B subset of A closure intersection Y. So we are done. So thus B equal to A closure intersection Y. That is the simple proof. Okay, now see the proof. Do you have any problem on this? Yes? Or is this fine? It is a simple one actually. Say something.
Fine, sir.
Right. Now there are few more properties. Actually, you will find some properties in the assignment as well in the tutorial sheet. You just try to solve that. Okay, so these are very simple. Now we define another concept called Hausdorff. That is very important. It is not only it is important for this course. In fact, this is important in general. That's mean in every topic you need this property of Hausdorff in any field of mathematics. So this is a very important concept in mathematics. Okay. So what is Hausdorff? So a topological space X is said to be Hausdorff if for every pair of points okay if you choose any 2 points in X, so there exist open sets say Ux and Uy containing X and Y respectively such that Ux intersection Uy equal to empty. That's when a topological space X is said to be Hausdorff if for any 2 points X, Y, you will find two disjoint open sets containing them. That's when say this is X, say this is Y. So that's when you will find two disjoint open sets containing them. Okay. Now can you give me one example of Hausdorff topological space?
Discrete.
Discrete. What about our usual topology in R?
Every metric
Sir, it is
space.
Hausdorff.
Right. In fact, every metric space is also Hausdorff, right? Okay. Now can you give me one topological space which is not Hausdorff?
in discrete
In
topology.
this,
Right. In discrete topology, in fact, you can also prepare now many topologies, right? You can take R and say co-finite topology. That is also not Hausdorff. Now there is an important theorem. So let X be a Hausdorff topological space. Okay. And let Xn be a sequence in X. Now then Xn, that is the sequence, converges to at most one point. That is very important. It says that if you have a Hausdorff topological space, and then if you take any sequence which is say convergent in the sense that converges to a point, okay, then the limit is always unique. That's mean a sequence converges to at most one point. Okay, but if a topological space is not Hausdorff, a sequence may converge in 2 points or more than 1 points. For an example, if you take in R, take co-finite topology and take the sequence xn equal to 1 by n. Now can you tell me where the xn sequence converges? In at which point? Yes, xn converges to which point? Okay, if it is usual topology, then xn converges to at which point?
eventually constant.
No, I'm saying that where xn converges, at which point?
In usual topology, it is converges to 0.
Right, and in cofinite topology?
All are
All the points.
Right, all the points. Why? Because if you take any point in R, say any point A in R, okay? Now, if you choose any points in R, then if you take any open set U containing A, right? Now, what does it mean? U open set? U open set means that R minus U is finite, right? And R minus U is finite means after some stage, that means there exists a natural number n such that xn belongs to U for all n bigger or equal to n, right? So that's when xn converges to A. So we are done actually. So that's mean whenever if you take cofinite topology and if you take this one, then it converges to any real number. Now similarly, in a real line, you can construct a topology such that, and you can construct one sequence so that that sequence converts to exactly 2 points. The sequence converts to exactly 3 points. It is fun. You can just do that. You can just take R and find a topology and show that it converges to 3 points, say exactly 3 points. Okay, you can define a topology in such a way. You should try that one. Okay, now we will prove this one. So if x is Hausdorff, then xn must converge to exactly 1 point. As we know that in our when we read that calculus course, then we have seen that that sequence, that limit point of a convergent sequence is unique. Do you remember that? We proved that. We proved by that epsilon criteria, right? We take some epsilon and we take two L1 and L2, and we show that mod of L1 minus L2 less than epsilon. So that's mean they are equal, right? But if X is not right, if X is not Hausdorff, then that may not be true. So anyway, now we prove this theorem. So that's when if X is a Hausdorff topological space, then Xn converges to at most 1 points. So first of all, let say what shall I take first? Okay. So let, if possible, Xn converges to X. Okay. First we assume that Xn converges to X. Now then, for any open set U, remember that for any open set containing X, right, there exists a natural number n such that Xn belongs to U for all n bigger or equal to n. Okay, this is true. I know, and this is true for any open set. Remember that. Okay. Now we will use actually this definition. Now let Y any other point, that is Y be a point in X, in the topological space X other than the element X. Okay. Now then there exist Ux and Uy, that is you can say open sets Ux and Uy such that X belongs to Ux and Y belongs to Uy, and Ux intersection Uy is empty. Why? Because X is Hausdorff. Right? Now that implies, so there exists a natural number n such that Xn belongs to Ux for all n bigger or equal to n. Right? Now that implies Uy, which is a open set containing Y, may contain at most finite points. Finite, we can say member of this. So that implies Xn does not converge to Y. So thus we can say that Xn converges to at most 1 point. At most 1 point. Is that clear? So we first assume that Xn converges to X. Now we assume that Y be any other points, right? Now since X and Y are different and X is capital X is Hausdorff, so there exist two open sets U and say V or Ux Uy such that their intersection is empty and Ux contain X and Uy contains Y. Okay. Now since Xn converges to X and Ux is an open set containing X, therefore there exists a natural number n such that all the elements after some stage belongs to Ux. Okay, so therefore Uy may contain only finite number of elements. So therefore, but it is a open set containing Y, but it will not contain all the elements of Xn after some finite stage, right? So therefore Xn will not converge to Y. So we are done. So that's mean Xn, if it converts to X, then that is only 1 point. Is that fine?
So does the converse holds?
Converse hold means
Like if we take any sequence that will have only at most one limit, then can we say the space is Hausdorff?
that is a good question. Okay, now let you think that one. That is a good question. Now he says that if every sequence xn in a topological space X converges to an unique point, if convergent actually, it may be divergent, then is X Hausdorff. Okay, so that is a good question. Now try to give one counter example if you feel that it is not true. Okay, that is a very good question actually.
Sir, I think this is not true.
Okay, can you give counter example?
Sir, if we take the co-countable topology on say R, then it is not Hausdorff, but I think wherever the sequences, if the whatever sequence converge, they are eventually constant.
Right.
So either the sequence do not converge at all, or if they do, then they are eventually constant. So their limit is unique, but it is not Hausdorff.
Right. So that's mean if you take only convergent sequence, then it should be a only constant sequence, right?
Yes, sir.
Okay. So not true. Example. Co-countable topology. Right. So if you someone don't get the proof, just think about that. And also try to find any other example other than this co-countable topology. So this kind of problem is very interesting. So whenever you see some statements, you always try to see that is the converse is true or not. Right. So this kind of questions are open. That's when you have to keep in mind that. And if you can solve and if you can find those counter examples, then that's when you will this will be very helpful for you. And again from this, so can you tell me that this is true or not in any Hausdorff topology? Singleton sets are closed. Can you prove it? If you have a Hausdorff topological space, then Singleton sets are closed. Can you give a quick proof of that?
Sir, we have to show that the complement is open. So it will be x minus a, and we take an arbitrary point. Suppose we take y.
Right.
We take y,
Then
then
x not equal to y.
so by the Hausdorff property, there exists an open ball which does not intersect with x. So it is contained in R intersection, R minus x.
Yeah, you can take x minus x, that one. Right. So you can take ux intersection ey is empty, right? No, now here you can check that uy subset of that. Right? So therefore, this is actually good exercise. That means singleton sets are closed, and from this you can say that any finite sets are closed. That's mean if you have a topological space, then if you Hausdorff topological space, then if you take any finite set, then that is also closed, right? Because singleton sets are closed. Okay. Now, which continuity definition we use? So first of all, here we generally use the definition of continuity. So a function f from x to y is continuous if for any open set u in y, f inverse u is open in x. So we will use this definition of continuity. Okay, so a function will be continuous if for every open set u in y, f inverse u is open in x. And also last time we have proved that actually. So if we take say projection map x cross y to x defined by pi1 xy equal to x, this is continuous. Why? Because pi1 inverse say u will be your u cross y, and if u is open in x, then pi inverse, that is pi inverse u is also open in x cross y. So that is open. So therefore pi1 is continuous. Similarly, you can prove that pi2 is continuous as well, right? So we have given that example. Now the question is, so if you have a topology, you have a large number of open sets, right? Now how to prove that a function is continuous? So can you give me a minimal possible sets, means subset or minimal possible collections from the topology, so that if we can check that this property is true, then you can say that f is continuous. So that's mean what I'm saying, that now give me a collection where if we check that f inverse of u is open for that collections, then it is sufficient to say that f is continuous. We don't need to check for every open set. Can you give me that collection?
The basis.
Right, basis. This is one. Now can you reduce that collection also?
The basis.
Right, that sub basis also will work. Now why it is work? Because it is the beauty of my f inverse. Because if you know that property of f inverse, you can see that satisfies actually some beautiful properties. Anyway, so which we need here. So first of all, we prove that. So let S be a subbasis for a topological space X. Now if, okay, X. Now let f x to y be a function. Okay. Now if f inverse, oh, topological space in y, not in x. Now if f inverse say s, okay, better to write f inverse u. F inverse u is open for any u belongs to that s, then f is continuous. Okay, now why that is true? So the proof is very simple actually. So proof. So first of all, so let B be a basis for the topology of Y. Okay. Now then B can be written as S1 intersection S2 up to Sn, where now Si belongs to that set S, that subbasis. Now that imply F inverse of B. Now that is the beauty of that inverse. If you know that set theory, you can easily prove that that is same as that's mean if you use that inverse, so you have equality here. Okay, and since each of F inverse Si is open, so therefore F inverse B is open. So this is one part, and also now let U is any open set in Y. Now then U can be written as union of any arbitrary collection U alpha, where you can say B alpha, where B alpha belongs to that basis. Basis. Now that imply again F inverse U. Again we have this equality. Union of this F inverse B alpha. Now because of that, now since each of F inverse B alpha is open, so therefore F inverse U is open in X. So that implies F is continuous. Okay. Now that is very important. That will be useful. So that's mean to check that a function is open. Okay, it is sufficient to show that inverse image of any subbase element is also open. It is sufficient to show that. We will use this fact later. Okay, so today only we will use this fact. Okay, so is there any doubt up to this? Yes? No, right? Okay.
So
Hmm.
yes, I have doubt in the previous argument, like the counter example we gave. It's more of a like a artificial type example. Like, can we impose some conditions on the sequences such that a given space will become Hausdorff? Like, I'm looking for some equivalent criteria.
Right, right. No, that see, these kind of questions are good questions. So I do not know any immediate answer. Even when someone says, I knew that that is not true, but I did not remember that counter example. That is the reason I gave you that you can think that will be a good exercise. And which you are asking now, this is also a good one. So we expect this kind of questions, but I do not have any quick answer. Currently, that's mean do not have any ready-made answer. So if I think, then I will get maybe, but I do not have any straightforward answer to give it now. Now think about that. That is also a good one. So can you impose some extra conditions so that that sequential criteria will be equivalent to that? So these are very good questions. So you have to think about that. Even I have to think about that. Okay, just think. If you get,
Okay.
then you can also let us know that okay, I think this one in this way. If this is true, then this will be true. So you students have to come forward and you have to think some reverse theorem. And if you get something, then also that is share with your batchmate as well. That will be benefited for all of you. That's when if you get something, if you share, if some other student gets something, if they share, that's when your knowledge will be increased. That is the beauty of the discussion. Okay, again think if you get something, then you just let us know. Okay.
Okay, sir.
Okay, and anyway, so if you have this kind of problem, if you want to discuss, then after the class time or other than that, we can discuss. Because to think of this kind of solution, we need time, right? So we cannot spend time during class time. Okay, so there are some more definitions. One is homeomorphism. So do you know the definition of homeomorphism? Do you remember that? I think it was in calculus course. So this is bijective, right?
F is
And
continuous, F inverse is
right,
continuous.
F and F inverse both are continuous. So this is in another way to say that now F is bijective and U is open in Y if and only if U is open. Oh, open in X if and only if U is open in Y. So this is the another one criteria. Okay. Now also try to think that these two are equivalent. How to show that both are equivalent. So this is one homeomorphism. Another one is open map. Now open map means F is X to Y such that image of open set is open. It is some kind of in reverse of the continuous function. Okay, so it says that I'm not saying that inverse image of open set is open. It says that image of open set is open. Okay, so this is called open map. So it does not require continuity. Okay, and another one is closed map. Now it says that if X to Y says that image of closed set is closed. Again, so no relation with continuity. And also these may not be bijective. Okay. So for an example, a function can be continuous and open both, but not homeomorphism because the function may not be bijective. And if it is bijective and continuous and open, that's mean it is by this condition, you can say that it is homeomorphism then. Okay. So no relation with continuity and no relation with bijective as well. Right. Now these are the definitions. You will actually find some applications of this one later in this course. And another important, that is the very important again in whole mathematics course, that is called pasting lemma. Now first of all, now I do not remember, did I prove that? So if Y is a closed set in X, suppose this, then a set C is closed in Y. Now we will imply C is closed in X as well. Can you see that? First of all, can you quickly prove it? If C is if Y is a closed set in X, that's mean A closed, you can say subspace. Then A set C is closed in Y, that will imply C is closed in X.
So C will be some C dash intersection Y.
Yes, C will be say some D intersection Y, say that one.
Where D is closed.
Right, where D is closed in Y, Y is closed, sorry, D is closed in X, Y is closed in X, so that part it is closed in X. So we are done, right? And similarly, we can prove that this one as well. If Y is say open subspace of X, then any U is open in Y will imply U is open in X. And similar logic, right? Since U is open in Y, therefore U can be written as V intersection Y, where V and Y both are open in X. So therefore U is open in X. So both are simple. Now by actually using this, we use the pasting lemma. Now what is the statement of that? So let F A to Y and G B to Y B to continuous function. Okay, and let A and B be to closed subset in in X such that X equal to A union B, and also given that Fx equal to Gx on A intersection B. Now then you will define a new map H from X to Y such that Hx equal to Fx X belongs to A and Gx X belongs to B union B. There is some noise is coming. Okay, now it is fine. Then it is continuous. Then we prove that H is continuous. Okay, now this proof is actually very simple. Why that is simple? Actually, the statement says everything. So there is nothing to prove. The statement says everything. So first of all, let U be an open set in Y. Okay. Then what is my H inverse U? That will be F inverse U union G inverse U. Just check that because that is just simple shape theoretic argument. Okay. Now F inverse U is okay. No, the problem is you have taken closed set, right? So now we have to reverse the proof. Okay. So first of all, we cannot prove via this one. First, we need another theorem actually. Okay. Now this one, can you see that f is continuous for any function, continuous if and only for any closed set C, f is some x to y. So for a closed set C in y, f inverse C is closed in x. So that is the equivalent criteria. Can you see that? It is true because f inverse y minus c will be x minus f inverse c. And similarly, okay, now this. So that's mean now let so C be a closed set. That's mean closed set in y. So that's mean y minus c is open in y. Now since f is continuous, so therefore f inverse y minus c is open. So that implies x minus f inverse c is open in x. So that implies f inverse c is closed in x. So this way you can prove this part, and similarly you can prove the other part as well. For the other part you need to prove that one. So for any open set u in y, f inverse that y minus u, that is again x minus f inverse u. So this. So therefore you can prove this. So okay, now we need to prove that f is continuous, right? Now you let u be an open set in y. Okay, then y minus u is closed. Now given that f inverse y minus u is also closed, now that implies x minus f inverse u is closed in x. That implies f inverse u is open. So thus f is continuous. So therefore it is equivalent actually. F is continuous to show that inverse image of any closed set is also closed. Okay, so do you have any doubt on this? That is very simple. Yes, any doubt? Or it is it fine? Okay, say something. What?
Yes, sir, it is clear, sir.
Good. Now we will prove this one. Now what we will take? We will take C. Now proof is simple. Now we will take a closed set in Y. Okay. Then H inverse of C will be F inverse C union G inverse C. Now F inverse C is open in A is open in, sorry, F inverse C is closed in A and A is closed in X. So therefore F inverse C is closed in X. And similarly for G inverse C is also closed in X. So therefore their union is closed. So H is continuous. So we just prove this here. So let C be a closed set in Y. Then H inverse C equal to F inverse C union G inverse C. That is just say theoretic argument, right? Now F inverse C is closed in where? Closed in A. Why? Because F is continuous. And also given that A is closed in X. So therefore F inverse C is closed in X. So this is one part. Again, G inverse C is closed in A. Why? Because G is continuous. Now again B in B. Now again B is closed in X. So therefore G inverse C is closed in X. So therefore H inverse C is closed in A, so closed in X. So that implies H is continuous. So we are done. And this is the proof.
If A and B are open, then it's true now.
Right. Now that is my question. Now suppose it is given that this is two continuous function and these two are open, and this is again intersection this, then F is continuous. Now can you prove that? Then again you can prove that. In that case, what you prove? You will prove in this way that H inverse of take with U, start with open set U. So let U is an open set in Y. Therefore, H inverse U will be F inverse U union G inverse U. Okay. But now tell me why that pasting lemma written as a open set, as a closed set, not in open. Why? That is the standard argument, not the open one. Do you know why? That is, it is easy to tackle. For an example, when we say suppose continuous in dimension 1, what we find? We take generally a closed set, this to this, right? And then we take another function set, this to this. And this is a closed set, this is a closed set, and they have share only one point, and which is also closed. So therefore, that function that if we take like this, then that will be continuous. So that is the reason generally the pasting lemma is stated as a closed subset. Because if it was stated with open subset, then generally it looks like if X is it looks like kind of this kind of intersection should be there. So in some sense, if you write in terms of close, it looks like little bit stronger. Means both are equivalent statement, but actually if you write in sense of close, then it is easy to apply. Because if you apply for this one, you can apply for the open one as well. But if you apply for the open one, then you have to something you have to derive to use in the closed one because of that intersection. Right? For an example, we can use pasting lemma in this sense that say x say 0 less than equal to x less than equal to 1, and say 1 less than equal to x less than equal to 2 in this way, because this shares only one point here. Okay. Fine. Now that is very useful one, pasting lemma. Right. Now in the last day, I talked about that if we have say arbitrary product. Say any arbitrary product, this one, while lambda is any index set, any. It can be finite, it can be infinite, it can be uncountable, it can be any. There may not be any order. Okay, this one. So we generally write x belongs to this, means x can be written as some x alpha. Alpha belongs to this. Okay, this one. Now there are two ways to give topology on this space. So let x alpha be a topological space for each alpha. Okay. Now there are two ways to give topologies in this. So first one is called box topology. That's mean basis element is of the form just this product u alpha, where u alpha belongs to say tau alpha. So with topology tau alpha. Right now, if now you can check that this forms a basis and it is called box topology. Now what is product topology? Now product topology is, it has basis element is in this form. Basis element is of the form this u alpha, where this u alpha is equal to x alpha for all except finitely many values of alpha. So what is the main difference? If you take u equal to that product u alpha, where u alpha is strictly proper set, proper open set x alpha, and u alpha belongs to tau, then u is open in box topology, but not open in product topology. Okay, so that's mean box topology is strictly finer than the product topology. Okay, now I told you last time, so why we have this kind of topology, these two kinds of topology. It is the because of, see, which you feel in general, that is the general one. That means suppose you know the topology of R cross R, then which one you feel the generalization of that, box or product? Which one you feel that should be the general actual that generalization, box topology wala or product one?
Box topology.
Okay, you feel box topology, right? Because for the box topology we use that one, that pi, that open sets of the from u cross v, where u and v both are open, right? We did not have any restriction. Where in product topology we have some restriction. right?
So I think for finite product, both topology will be same.
Right. For finite, both are same. For infinite, okay, I should write here, right? Is strictly finite in product topology if that index set is infinite, right? I should mention that. Good point. Okay. Now note that. Now this is the generalization of this one. Now why product topology is a generalization actually? Now note that. Now tell me what was the subbasis for x cross y. What was the subbasis for x cross y in terms of projection map? Do you remember that? What is the subbasis for this product x cross y? It was, okay, I should write now in this way, pi 1 inverse u and pi 2 inverse v, where u is open in x and v is open in y. Do you remember this collection forms a subbasis for the topology x cross y? Do you remember that?
Yes, sir.
Okay. You should not forget. That is the most important thing. Okay. Now that was the subbasis for this one. Now suppose we have this product x alpha. Okay. Now if we write this one, that is say s equal to that all the collection by beta inverse say by say alpha and inverse u alpha, where u alpha is open in x alpha, where alpha belongs to that collection, this one. Now if you take this collection, now tell me S is a subbasis for which topology? Product topology or box topology?
Product.
Right, it should be, it is a subbasis for product topology. Why? Because in our case, what was the basis of product topology? B was some B1 say cross B2 in terms of this one B3, and all the element was this x4 x5, say this one example, right? And in this case that was your pi 1 inverse B1 intersection pi 2 inverse B2 intersection pi 3 inverse B3, this one. Or in general sense, I should not write in this way, it may not be a countable product. Now say B equal to say product of U alpha, where U alpha 1, alpha 1, U alpha 2 up to U alpha n, where proper and remaining are whole space. Whole space. Then B is actually now pi alpha 1 inverse U alpha 1 intersection this. Okay, so this is the D space. So that is the region. Remember that. Now if you need one kind of subbasis, this kind of projection map, by this projection map, you cannot give a subbasis for the product topology. Sorry, subbasis for the box topology, but that will be your subbasis for the, this S will be subbasis for the product topology. Okay, that is the reason this is very important. So if you generalize X cross Y in terms of this subbasis, then product topology will be your generalization. And if you want to generalize the product in terms of the topology, then box topology will be the generalization. So this way they are different. Okay. So this is generalization via subbasis, and this was via basis. Right? Now you have a X, you have a subbasis for X cross Y, the standard subbasis. Now if you generalize via subbasis, you will get product topology. Now again you have a basis for the product topology. And if you generalize via basis, then you will have box topology. Did you get my point? Yes or no?
Yes, sir.
Yes.
Okay. Okay. Now there are two important, actually not two, we can say just one. That is theorem. This is the last one. Okay, please. So do you have any class from 3:30?
Yes, sir.
No, sir.
Huh? Yes or no?
No, sir.
Okay, so just wait, because anyway I will not take up to 3:30 because we need to discuss about the quiz, because we will have quiz right in this Sunday. So we'll have to fix the time and mock for the mock test as well. So let me first finish this theorem. That is one. Now it says that, now if you say if, say product of x alpha to say x is a function such that, okay, no, say x to x alpha such that f of x is given as f of x, f of alpha x. Okay, in this way we define a function f. Now let product of x alpha has product topology. Okay, now then f is continuous if and only if each of f alpha is continuous. Now the proof is straightforward by applying f alpha equal to pi alpha compose f. Okay, now see, if f is continuous, now that implies f alpha is continuous, right? Because it is composition of two continuous functions. Now conversely, now given each of f alpha is continuous. Okay, now we need to prove that f is continuous. So how to prove f is continuous? We take inverse image of any subbasis element. Now f inverse image of any subbasis element, that will be f pi alpha compose f inverse u alpha equal to f alpha inverse u alpha. Now again this is open as f alpha is continuous. That's mean inverse image of any subbasis element is also open. So therefore F is continuous. And this is subbasis element. Okay, that is very simple one. Now this result is not true if we use here product topology, a box topology. Now this result is not true if we have product topology. No, sorry, box topology. For an example, take R omega. What is R omega? R omega is the standard notation for this. R cross this. That is countable product of R. Okay. So that is the standard definition of R omega. So now if we define F from R to R omega defined by F of t equal to t comma t comma t in this way, then say that is my f1t, f2t in this way. Then you can see that each of fit, that is t, and that is continuous, right? Because it is just an identity function. But f is not continuous. Why f is not continuous? We can give one open set whose inverse image is not open. Now can you give me such open set whose inverse image is not open? We can take u equal to say minus 1 1 minus 1 by 2 1 by 2 this way. Now what is f inverse u? Now you can check that f of 0 equal to 0 0 0 in this way belongs to u. So that implies 0 belongs to f inverse u. Right? Now if f inverse u is open, so there exists epsilon positive such that 0 belongs to that minus epsilon comma epsilon subset of f inverse u. Right? Which is the definition of open set. Now that will imply f of minus epsilon comma epsilon subset of u. And that's mean minus epsilon comma epsilon. You can, if you apply pi I f minus epsilon comma epsilon subset of say pi I u, say pi n. Now that will be minus epsilon comma epsilon. Now that will be subset of, now pi n of u will be what is that?
minus 1 by n.
Right, 2 comma 1 by n. That, but that is a contradiction. Contradiction, because epsilon is a fixed number, but this is true for all n actually. So it cannot be true. So that is not a continuous function. Okay, and what is actually f of minus epsilon comma epsilon? That is this one, minus epsilon comma epsilon product with this in this way. So that cannot be subset of this open set. That's all. Okay, so we are done. So anyway, I will upload the notes now only. You can see, and also I will upload the text, that video file as well. So go through that. If you have any questions, anyway, you can ask me in the next